Hello, this is Miss McBride. We're going to be talking about best fit lines and prediction, section 7.3 from Statistical Reasoning for Everyday Life. Our learning goal here is to become familiar with the concept of a best fit line by understanding what it is, being able to analyze it and draw it, and look for a correlation. Recognize when such lines have a predictive value, because they don't always. Sometimes they have limitations, and understand how the square of the correlation coefficient is related to the quality of the fit. And then qualitatively, in other words, we're going to be understanding the use of multiple regression, but we aren't going to do computations on it, hence qualitatively understand. First thing we need is a definition. What is a best fit line, also known as a regression line? This is going to be a line on a scatter diagram that lies closer to the data points than any other possible line, according to the standard statistical measure of closeness. In other words, we're going to be drawing a line. We can visually draw it by taking a ruler if I have a scatter plot, or I have a graphing calculator video that shows you how to do it right on the graphing calculator. There are mathematical formulas for finding the equation of that regression line, and that's what we're going to skip. They're very long and nasty. We will use the calculator or computer to do it for us. So please have your TI 83 or 84 ready for use. We will be using it at the end of the lesson. I do want to do a little review of algebra before we go on, and how to use it to graph a line. So remember, a line has two components, the slope and the y-intercept. The slope is the slope, statistically speaking, of a regression line is the coefficient, remember that's the number in front of, the explanatory variable, which is going to be our x variable, and tells us the amount of change in the response variable, the y variable, we can expect from a 1 unit change in the explanatory variable. So that's what a slope is. Remember, it was a ratio of rise to run from your Algebra 1 class a long time ago. The y-intercept of this regression equation is the value of the response variable, or the y variable, we would expect when the value of the explanatory variable, the x, is 0. So if you dig back in your memory to Algebra 1, if you kind of visualize this grid on an XY axis, the y-intercept is up on the y-axis because that's where the x value, the explanatory variable, is 0. The slope is the rise over the run. If it goes up and over, you have a positive slope, which we're talking is a positive correlation. If it goes down and right, it's a negative slope or a negative correlation. On our TI 8384, the linear regression line, lin-reg, is in the form y equals a plus bx. That's a little backwards than you might be remembering from algebra. So a is the y-intercept, and b is the slope. So when we look at this a little later on your graphing calculator, it will show you this up at the top. It'll say y equals a plus bx, and a, remember, is your y-intercept, where it starts, and b is the slope from there, the rise over the run. So how do we use this best fit line to make predictions once we've found it? Well, first let's talk about some cautions. Once we get the equation, it's pretty straightforward. But what are some of the cautions we have to think about? First off, don't expect a best fit line to give a good prediction unless the correlation is strong and you have many data points. If the sample points lie very close to that best fit line, they're tightly clustered, then the correlation is very strong and the prediction will likely be accurate. Because remember, we're going to run a line through the middle. So we're using that simple line to make a prediction. So the closer the points are to that line, the stronger the prediction. If the sample points are scattered all over the best fit line, the correlation's pretty weak and the predictions tend to be much less accurate. And we'll see some pictures in a minute. Second, don't use the best fit line to make predictions beyond the bounds of the data point to which the line was fit. We have a good example of that in a minute, but you're within a certain range. You can't, like if you're within 10 years, you can't make a prediction for 100 years later. That takes us to our third point. A best fit line based on past data or historical data is not necessarily valid now and might not result in valid predictions of the future. So if you're looking at things from 20 years ago, you can't really use them to predict into the future or currently. It has to be fairly within the current time frame. Fourth, don't make predictions about a population that's different from the one from which the sample data was drawn. The prediction should be based on a member of the population that was used to construct the best fit line. And we'll see an example on that in a minute, like taking something that happened in Asia and trying to use it to predict behavior in the United States. Totally different culture and population, so the results might not transfer over to a different culture. And last, remember that a best fit line is meaningless when there's no significant correlation or when the relationship is nonlinear. So we're going to be calculating that correlation coefficient. If it's 0, my best fit line doesn't mean anything because there's no correlation, or it could be nonlinear. So let's take a look at some examples and which of those 5 things we are using to make the valid prediction, or state whether it could work or not. So, state whether the prediction or implied prediction should be trusted in each of the following cases. Why or why not? So, can we trust our prediction? You found a best fit line for a correlation between the number of hours per day that people exercise and the number of calories they consume each day. All right, that should be a fairly strong positive correlation. You use this correlation to predict that a person who exercises 18 hours a day would consume 15,000 calories. Problem: nobody exercises 18 hours a day on an ongoing basis, so this much exercise would be beyond the bounds of the data collected. So this could not be trusted. It's way beyond the bounds of what people exercise. How about there's a well-known but weak correlation between SAT scores and college grades? That's very true. You use this correlation to predict the college grade of your best friend. Well, if it's weak, it's still okay, but it's not going to be a super accurate. So the fact the correlation between SAT scores and college grade is weak means there's much scatter in the data. If I drew my line through the middle, they're scattered all about. As a result, we wouldn't expect great accuracy, but I can use it, to get an idea for an individual. How about historical data? Ooh, as soon as I see historical, I start going, oh, I don't know about that. Have shown a strong negative correlation between national birth rates and affluence, how wealthy they are. So countries with greater affluence who have population that has more money tend to have a lower birth rate. Use this data to predict a high birth rate in Russia. Well, we can't assume, first off, the historical data will apply today, and in fact, Russia now has a very low birth rate despite having a low level of affluence. In China, they discovered correlations that are useful in designing museum exhibits that Chinese children enjoy. A curator suggests using this information to design a new museum exhibit for Atlanta area school children in the United States. Not a good idea. The cultural differences between China and Atlanta suggest that this is not from the member of the population for which the data was derived. So that would not be a good idea. I would not trust it. How about a scientific study showing a strong, very strong correlation between children's ingesting of lead and mental retardation? Based on this, paints containing lead were banned. This is very true. The strength of the correlation and the severity of the consequences, this prediction and the ban that followed seem quite reasonable. In fact, later studies actually did establish lead as an actual cause, not just a correlation, but a cause of mental retardation, so the rationale behind the ban was even stronger. So this is a good one because it's a strong correlation. The data was clustered tightly about the best fit line, So and there was a lot of data. So this one is a good study. I would use the prediction. Based on a large data set, you made a scattered diagram for salsa consumption per person versus years of education. I love these ones they come up with. So the diagram shows no significant correlation, as would be reasonable, but you drew a best fit line anyway. That line predicts someone who consumes a pint of salsa has at least 13 years of education. Well, because it was meaningless, it doesn't matter. So, no significant correlation, best fit line, correlations are useless, meaning. So let's go ahead and take a look at this correlation coefficient and the best fit line now that we have an idea of what it is and some of the cautions about using it. We have a correlation coefficient R, remember that. If we square it, we get R squared. That's going to give us another value. It's going to give the proportion or the percentage of the variation in a variable that's accounted for by the best fit line. Now the reason we square it is we want it to be positive. This thing is called the coefficient of determination. When we look at how tightly clustered my data is, the higher the R value, the higher the R squared value. So the percentage of variation accounted for, in other words, I've got it in my best fit line. So when I have those outliers out there, my coefficient of determination is going to be kind of small because I got guys that are way away from the best fit line. The more tightly clustered they are, the higher the R squared value. So political scientists are interested in knowing what factors affect voter turnout in elections. So this is your example 4 from your section notes you should be filling out. One such factor is the unemployment rate. Data collected in the presidential year since 1964 shows a very weak negative correlation. So between voter and unemployment rate. So as one goes up, the other goes down. As the unemployment rate goes up, the voter turnout goes down and vice versa. So that's your negative, and the correlation is negative 0.1, almost 0. Based on this correlation, should we use the unemployment rate to predict voter turnout? So we know the correlation is weak, but we need to take a look at the R squared value, the coefficient of determination, to determine. It's a good name. So the square of this gives me 0.01, which means that only 1% of the variation in the data is accounted for by that best fit line. Therefore, 99%, almost all the rest of it, is explained by other factors. Hence, we can conclude that unemployment is not a reliable predictor of voter turnout, where unemployment was my explanatory variable and voter turnout was my response variable. So that coefficient of determination, it helps me determine whether this is a good predictor based on the variability accounted for in the best fit line. Right, so here's our fun data again from 7.1 on the diamonds. We're going to take a look at what's called multiple regression. The last one was a single regression. What if I have a multiple regression? I want to use it to calculate the best fit equation where I have one response variable, but I have a combination of 2 or more explanatory variables. A couple different things could be going on. Now this is why I have you watching the stat talk video called confounding, because remember, confounding variables means I've got more than one thing going on and I can't get them separated out. So what if I want to take a look at 2 or more explanatory variables? I want to see what's going on at the same time and how they affect my one response variable. Again, I'll use the coefficient of determination, but notice I now have a capital R squared. That tells us we're using a multiple regression. I think of it as I got a bigger, number of explanatory variables. A single R is when I have one explanatory variable. Now this one we're not going to do in our graphing calculator. This takes some fancy software to do, but they can give us the R squared value and we can account for the proportion of scatter in the data. So if R squared again is close to 1, now this is true whether it's a single or multiple regression, the relationship is strong and the information is useful, or the prediction line is useful. If R squared is close to 0, I have a weak relationship and it's useless. Now here I'm not saying linear because these are not necessarily linear for the capital R squared because I got multiple, but same idea for the single. All right, so let's take a look at some examples here. They didn't really give me too many scatter plots to look at, so I'm going to do some examples on that on the next slide. Okay, number 1, let's kind of go over what we've talked about. Best fit line. What is it and how is it best fit line useful? Well, it's a regression line. It takes my data and it runs a single line through the scatter plot that I can use to predict. I can use it if my R value is strong enough or my R squared value is closer to 1 to make a meaningful prediction. Number 2, little r squared just means I have one explanatory variable. For a study showing paired sample data, it's found that the correlation coefficient R is -0.4. What is the value of R squared, the coefficient of determination? Well, if I square that number, I get 0.16. In general, what is it called? We said that. What does it measure? It measures the variability that's accounted for by the best fit line. And how can it be interpreted? So this value here, if R squared is 0.16, that means that 16% of my variability is accounted for. So it's not a very good predictor. That's a pretty low number. Number 3, talking about regression. So our investigator here has data consisting of heights of daughters and heights of the corresponding mothers and fathers. So here I got 2. She wants to analyze the data to see the effect the height of the mother and the height of the father. So I need a multiple regression because I have 2 explanatory variables. So she should use the multiple regression. What is the basic difference between linear regression and multiple regression? All right, so linear regression means I have one explanatory variable. Multiple, I have several for one response variable. In a linear regression, I'm looking for a line of best fit. Number 4, that capital R squared now tells me I'm using a multiple regression. So using data described back in exercise 3, it found that R squared was 0.68. So what does that mean? Interpret that. And what does that value tell us about the data? That means, sorry, I hit the wrong button. Okay, anyway, so we're interpreting that 0.68 tells me that 68% of the variation in heights of the daughters, because remember that was my response variable, can be explained by the variation in heights of mothers and heights of fathers, because those were my multiple explanatory variables. All right, does this make sense? Number 5, little r squared equals 1. Ooh, that's perfect. Is obtained from a sample of paired data with one variable representing the amount of gallons purchased and the total cost of gas. Well, that makes total sense. It has to be a perfect pairing because one directly results in the other. No variation about it. Number 6, r squared equals -0.40. Well, I don't even have to read the rest of it. Anytime you square a number, you can't possibly get a negative, so that makes no sense anyway. And we know that height wouldn't have anything to do with SAT scores. Number 7, height and weight. So using data from the National Health Survey, the equation of the best fit line for women's heights and weights is obtained. And it shows that a woman 120 inches tall is predicted to weigh 430 pounds. Well, this breaks my rule that says you're outside the bounds of your data. Even though I could have gotten their heights, what is it, 5 feet is 60 inches, so 6 feet is 72 inches. So if somebody's 120 inches divided by 12, that's 10 feet tall. I don't think so. So we cannot use this as a prediction simply because it's beyond the bounds of where the data will fall. So I could get good data, but then I cannot use it to make a prediction this far outside the data range. All right, I'm not going to do 8 because I couldn't get that. This is something they didn't show you how to do on the other part of the PowerPoint. So if you look at problem number 13, the instructions are above here, over to the left. So we're supposed to construct a scatter plot and based on visual inspection, draw the best fit line by eye. So what I did was I put the correct answer over on the right side, and then I made a video so you could see how to get that scatter plot. Now on your graphing calculator, when we do the zoom stat, it narrows it in so you don't get all the white space. So it'll cut it off somewhere closer to 60 on the X scale and up a little bit on the Y scale. So you'll see the part of that they have the scatter plot, or sorry, the best fit line drawn through. So I show you how to do that on your graphing calculator. Briefly discuss the strength of the correlation. All right, I discussed that on the video as well, but basically my R value, my correlation coefficient, is about 0.59, so that's a moderately strong, so we could use it to make some predictions. Based on my value for R squared, my R squared is 0.345. That means that about 35% of the variation, so here we can see the line and you can see the data is varying around it, a little above, a little below, that 35% of that variation in the death rate, because that's my response variable, can be accounted for by the linear relationship. So 35% accounts for the death rate, which means 65% is other factors, so that probably would not be a good predictor of death rates as your speed limit. Part C, identify any outliers on the scatter plot. Well, you've got that one at 75.61 out towards the end and up high, and then another one at 73.5, so those two are kind of one high above, one high below. But how would it affect the line? Because one's above and one's below. It wouldn't affect the line too much because they kind of cancel each other out. Part D, for this case, do you believe the best fit line gives reliable prediction? And I answered that one already. No. It'd be difficult to conclude the model is necessarily linear outside the range of the data because I have such a low coefficient of determination there. So high speed limits might cause the death rate to increase faster than indicated by the line, while lower speeds might cause death rates to decrease faster than indicated. This value of R, and hence R squared, is just too small to consider predictions based on the best fit line to be reliable. All right, I have another problem here I want you to try. I did not make a video of this one. I want you to go ahead and do it yourself. The data here is in exercise 20 of section 7.1, which I put at the bottom left. Remember, your explanatory variable is the birth rate. The response variable is the percentage change in population. So we did this one on the other section, so I thought it would be good to go back to it. Now take a look at it, looking at the correlation coefficient and the coefficient of determination. So I want you to do this one on your own. When you got it in your calculator, take a look at the plot that I have here. That's what you should get, and that should be your line of best fit kind of through the middle. You can see here that there's a weak correlation, well, moderate, 0.5. The data is scattered pretty high and low, so R squared is 25.25. So 25% of the variation can be accounted for by that best fit line, which means 75% is other factors outside of the birth rate. So this is not very reliable either. You want values much closer to 1 to make reliable predictions. Okay, please watch the video. It shows you how to use your graphing calculator to do this and makes life a whole lot easier. All right, thanks. Bye.